Atomic models. During the late 19th and early 20th centuries, several models of the atom were put forward due to extensive research and thought. The Dalton model of indivisible atoms from 1803 was found to be incorrect. The current model involves quantum physics, and it all started with Thomson and the discovery of the electron in 1904. Thomson's discovery of the electron was the first evidence that the atom had an underlying structure. He proposed that electrons moved within an atom of uniformly distributed positive mass and charge. Thomson's model for the atom was called the plum pudding model, since the electrons are distributed throughout some positively charged stuff, much like the English dessert where raisins are embedded in an egg suet and molasses mixture. The plum pudding model only lasted 5 years, until work done by one of Thomson's former students, Ernest Rutherford. Rutherford, Hans Geiger, and Ernest Marsden performed many experiments that fired a beam of alpha particles at gold foil. If the atom was like a plum pudding, the alpha particles would go mostly straight through, like this. All the positively charged mass of the atom would be evenly distributed throughout the entire atom, reducing the possibility of collisions. However, the experiment found that some of the alpha particles were deflected. Some even bounced straight back towards the alpha source. As Rutherford said, "It was quite the most incredible event that has happened in my life. It was almost as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." The conclusion: the positive charge must all be located in a tiny region of the atom, the nucleus. The mass is not spread out throughout the atom, it is very concentrated. Since all the positive charge of the atoms was concentrated in a small nucleus, most of the atom was just empty space. Consequently, most of the positively charged alpha particles would not be deflected by the positively charged nucleus. However, the small percentage of alpha particles that actually struck a nucleus were deflected, and in the most extreme case, just bounced right back. After analyzing the data, Rutherford proposed that atoms consist of a nucleus with a diameter of the order of 10 to the negative 15th meters, 1/100,000th the diameter of the atom, and the nucleus was surrounded by electrons in planetary orbits. Why do you think Rutherford proposed planetary orbits? The orbital model was probably chosen because of the similarities between the force equations for gravity and the electric force. Since the equations are similar, and gravity causes planets to move in orbit about the Sun, why wouldn't electrons do the same relative to the nucleus? Rutherford did not propose how the electrons orbited. That was left to Niels Bohr. To emphasize how much of the atom is just empty space, a void. If the nucleus was magnified so that it was the size of a baseball, then the atom would have a radius of 4 kilometers. The electrons would be the size of the period at the end of this sentence. The below website presents a great simulation of Rutherford's gold foil experiment. In this simulation, this PhET simulation, this is the atom. Here are the energy levels that the electrons can exist in. That yellow dot is the nucleus, and these red dots are flying through. These are the alpha particles that were shot at the atoms. If a gas is placed in a tube and a high voltage is applied to either end of the tube, the gas will glow. It will emit light. When this light is passed through a diffraction grating, each element displays a certain spectra that is unique. It has its own set of frequencies, some visible and some not, that can even be used to identify the element. The Rutherford model had no explanation for why this occurs. More on these spectra in the next topic. The electrons in the Rutherford model were kept in orbit by the Coulomb force, providing the centripetal force between the electrons and the positively charged nucleus. That was good. But the current electromagnetic theory stated that an accelerating charge would emit radiation. Since the electrons were constantly accelerating, centripetal acceleration, they would lose energy. This loss of energy would cause the electrons to slow down, fall out of orbit, and collapse into the nucleus within 10 to the negative 11 seconds. However, this doesn't happen, as evidenced by the fact that we're all still here. In 1913, Niels Bohr applied Einstein's concept of quantization to the Rutherford model to explain the optical spectra for atoms with only one electron. Helium missing one electron, lithium missing two electrons, etc. Bohr's model agreed very well with the experimental data. To the right is the Bohr model of the atom. The nucleus is shown in the middle, with electrons orbiting the nucleus in circular orbits. Keep in mind, this is just a representation. It is not to scale. Here is the Bohr atom. An electron is held in orbit by the Coulomb force, where Z is an integer representing the number of protons in the nucleus. For example, hydrogen has one proton, so Z would be 1. Niels Bohr made the following assumptions to address the shortcomings of the Rutherford model. It is called a semi-classical model, since Bohr combined classical physics with emerging quantum theory. Electrons can only revolve around the nucleus in certain circular orbits with fixed angular momentum and energy. The further away from the nucleus, the greater momentum and energy. When in these orbits, the electrons will not radiate electromagnetic energy and will therefore maintain their energy. Electromagnetic energy is emitted from or absorbed by the atom when electrons move between orbits. The energy of the emitted or absorbed photons is the energy difference between the allowed orbits. In this diagram, there are 3 orbits, N1, 2, and 3, that electrons can be in. When an electron falls from a higher energy level to a lower energy level, shown here in green, it emits a photon with frequency f that is proportional to the energy difference between these levels. In this diagram, there is an electron in the ground state, n equals 1. If it absorbs a low energy photon of exactly the right amount of energy, it can jump to n equals 2, shown with this purple arrow. If the electron absorbs a high energy photon of exactly the right amount of energy, it can jump all the way to n equals 4, the green arrow. We can represent these energy levels in a better way, with energy level diagrams. Keep in mind, this does not represent the actual distances or energy differences between the levels. This is just useful in comparing the planetary model to Bohr's model. The lowest energy level in the hydrogen atom represented to the right is the ground state, where n equals 1. If an electron at this level absorbs a photon with 10.2 electron volts of energy, it will jump to n equals 2. See how this is at negative 13.6, this is negative 3.4. The difference between these is 10.2 electron volts. So if an electron here absorbs a photon with 10.2 electron volts of energy, it will go here. If an electron up here at N4 emits a photon, releases a photon that has 2.55 electron volts of energy, well, it'll fall down to n equals 2. Ionization is when enough energy is added to completely eject the electron from the atom. The negative energy levels mean that the electron is bound to the atom. Here is an energy level diagram of a hypothetical atom with specific energy states. Sometimes the energy levels are described as negative, representing the ionization energy. The ionization energy is the amount of energy required to free the electron from the atom. Does A or B show photon absorption? A shows absorption. An electron at level n equals 2 absorbed a photon of light with 8 electron volts of energy and jumped to n equals 4. See how we are at negative 10 and then we end up at negative 2 because that difference is 8 electron volts of energy. B shows emission. An electron at n equals 4 emitted a photon of light with 3 electron volts of energy and fell down to n equals 3. See, it had this much energy, then it lost 3 electron volts, which brought it from -2 down to -5. Here's a quick tour through Bohr's mathematics. This is not covered on the AP Physics 2 test. The quantized angular momentum of each level is expressed as this equation here, where n is the number of the energy level. Remember, this is angular momentum, L. The Coulomb attractive force between the nucleus of charge Ze, that's the number of protons times the charge of an electron, and the single electron that provides the centripetal force, remember, Bohr was only calculating orbits for atoms with a single electron, is given by this equation here. So this is Coulomb's law. Combining these two equations, doing a little algebra, and solving for the radius of each quantum level, we get this equation. By using classical equations for the kinetic energy, potential energy, angular momentum, Coulomb's law, Newton's second law, and Bohr's quantum assumption, the energy of the quantum levels in hydrogen-like atoms is determined to be this equation right here. Most of the terms in the equation above are constants. We can combine all of the constants into one new constant called the Bohr radius, A0, which equals 5.29 times 10 to the -11 meters. The Bohr radius is defined as the electron orbital radius for the ground state of the hydrogen atom. Radii of other hydrogen-like atoms, atoms with only one electron, are expressed in terms of the Bohr radius, where n is the energy level of the electron and z is the number of protons in the nucleus. And by substituting in the values of the constants in the energy equation, it is found that this is the equation with the -13.6 electron volts out front. As mentioned earlier in the hydrogen energy level slide, the energy levels are all negative, indicating that the electrons are bound in the atom. The levels get closer together and closer to 0 as n increases. Limitations of the Bohr model. The model is applicable only to hydrogen-like atoms with single electron. The model is based on an assumption that accelerating charges do not emit electromagnetic radiation if they're in specific orbits. And the model predicts the frequencies of the photons that are emitted when an electron changes orbits, but does not predict their intensities. More work would now be done by Bohr and many other physicists to transition the explanation of atomic phenomena into a more complete quantum theory. One last thing, the nucleus has a structure too. With all these incredible theories and experiments in the first 25 years of the 20th century, it's interesting that the neutron's existence was not proven until James Chadwick demonstrated its properties in 1932. Ernest Rutherford, in 1920, proposed that a neutral particle with a mass on the order of the proton existed to account for the atomic mass measurements of atoms. Experiments were performed before Chadwick that actually found neutrons, but they were mistakenly believed to be gamma rays or even protons. Why do you think it took so long to discover neutrons? Because of the absence of charge on a neutron, it was impossible to detect with electric and magnetic fields in the way that made the discovery of the electron possible. Chadwick placed a small quantity of radioactive polonium in an evacuated chamber where it decayed by emitting alpha rays, helium nuclei, that then struck a beryllium target. Neutrons were emitted from this reaction and were found to have the correct mass and a neutral charge. Neutrons are essential to having more than one proton in a nucleus. More about that in the nuclear physics chapter.